Alright, it's Niaki osteozone. So today we are going to have a Niaki chemistry series, and today we are going to discuss on chemical bonding. So we have a lot of tutorials on our playlist, so you need to subscribe so that you'll be notified whenever we post, right? So we are going to have the tutorials of all the science subjects. We have a lot of tutors who specialize in different specialties, so we got you covered. What you only need to do is to subscribe to our YouTube channel, and always remember to follow us on our TikTok page. It's Niaki osteozone, right? And also remember to message the admin if you happen to have any question which you feel like it needs our attention, so that we can discuss the questions over here for the benefit of others, right? So today we are going to have chemical bonding, one of the fundamental concepts in chemistry, one of the building blocks of chemistry, right? So chemical bonding is defined with respect to the electrons, right? So chemical bonding is defined with respect to the electrons. So we said protons and neutrons, they make up what we call the nucleon number, which is also equal to the mass number. So the electrons doesn't contribute to the mass number, it only contributes to the chemical behavior, behavior of a compound, of an atom, right? It only contributes to the chemical behavior of an atom. So from A-level chemistry, that's where we are going to explain the effect of a proton or neutron on the chemical behavior. But as for now, just know that protons and neutrons, they only contribute to the mass number. Only the electrons contribute to the chemical behavior, to the chemical nature of an atom, right? As for now, just appreciate that for junior chemistry is enough, right? So the arrangement of electrons, the arrangement of electrons determines the chemical nature of an atom. So chemical reactions or chemical bonding is based on what you call the John Dalton's postulations, as I've alluded to before. So we are going to mention the John Dalton postulations again. So the first one, matter is made up of smallest particle called atoms. So matter is made up of smallest particle called atoms, right? And then the second one, different atoms combine in small whole numbers to make compounds, to form compounds, right? And then the third one says all atoms of the same element, have the same chemical properties, right? All atoms of the same element, they have the same chemical property, right? So we have what we call isotopes. So isotopes are defined as atoms of the same element. So we have isotopes. So you must take note of these terms, right? So isotopes are defined as atoms of the same element with the same number of protons, same number of electrons, but different mass numbers, or different number of neutrons, as we say. So different, so let me say neutrons first, but different number of neutrons which will result in different mass numbers, in different mass numbers, right? So isotopes, you should know the definition of an isotope by heart. You should know the definition of the term isotope by heart. Isotopes are atoms of the same element with the same number of protons, right? We are having the same number of protons, same number of electrons, but different number of neutrons, right? So what determines the chemical nature of an atom? We said these are the electrons. So if you are having same electrons, this simply means to say we are going to have same chemical property, right? So isotopes, they have the same chemical properties. Isotopes have the same chemical characteristics, right, or properties, right? So we say it from the John Dalton's postulation, atoms or atoms of the same element, they have the same chemical characteristics. And then we introduced the term isotopes, right? So at times they want to trick you, right, by saying we are having carbon 12 and then carbon 14. Comment on their chemical nature. These are isotopes. They have the same number of protons, but different, same number of protons, same number of electrons, but different mass numbers, right? Different mass numbers. So they have the same chemical property. You should take note on that one. You should take note on that one. We have chlorine 35 and then chlorine 37, right? So you should understand that. You should be able to, you should understand that. Are we together, guys? And then we go on to the last one, the last effect from Sir John Dalton. So the last one says, during a chemical reaction, when new compounds are formed, when new compounds are formed, atoms are neither created nor destroyed, but they are merely rearranged. They are merely rearranged. So this is what you need to know from the Sir John Dalton's postulation. So we are going to explain this one. We are going to explain this one when we are doing chemical equations, right? During a chemical reactions, atoms are neither created nor destroyed, but they are merely rearranged. So we are going to explain this one when we are doing chemical reactions. As for now, you need to master this one. These are the first three ones, right? And also to take note of this term isotope. You should be able to define the term, and you should be able to give examples. We have chlorine 35, and then chlorine 37, we have carbon 14, and then carbon 12. So carbon 12 is the one which we use in measuring relative atomic masses, relative molecular masses, relative isotopic masses, relative formula mass. So we're going to discuss this when we are doing stoichiometry, right? As for now, just appreciate. As for now, you need to have the appreciation, right? So we're now diving into the concept which we have been discussing, right? So we said that electrons are the one which determines the chemical nature, which determines the chemical nature, right? Are we together? Electrons are the one which determines the chemical nature. So we need to understand what is meant by the term electronic configuration. So we've discussed these terms before, right? Electronic configuration. So electronic configuration is defined as the arrangement of electrons in their electric shells. So in our series, I taught you how to write the electronic configuration, right? So we're going, let us say we are having, so this is a periodic table, right? So this is the periodic table. So from the periodic table, we understand that we can be able to write the electronic configuration, the first shell filled with 2 electrons, and then all the other electrons filled with 8 electrons, and etc. So all the atoms, they react to attain what we call stability. And then stability, all the atoms, they react to attain what we call stability, right? And then stability is found in group 8. Right? Group 8 elements or group 0 elements, they have what you call the stability. So all the elements, they react to attain what we call the stable noble gas electronic configuration. They want to have the same electronic configuration like that one of a noble gas. Are we together, guys? So you must understand this. You must understand this, right? Because this is where your A-level chemistry is being derived. So you need to listen very, very carefully. You need to know this by heart. right? So we are saying that atoms, they want to have the same electronic configuration like that one of noble gases, the group 8 elements. So these are the stable atoms on the periodic table, meaning to say all the other elements, all the other atoms are not stable, right? Since they want to be like these noble gases, they are not stable. So they are striving for stability, and then the stability is in group 8. So they want to have the same electronic configuration like the group 8 elements. They want to have the same electronic configuration like the group 8 elements. So they are going to react by sharing, by losing, or by gaining electrons, so that they will attain or they will achieve the stable noble gas electronic configuration. Are we together, guys? So the idea of chemical reaction or chemical bonding is to attain stable noble gas electronic configuration, is to have 8 electrons in the outermost shell. In other words, we want to have 8 electrons according to electron bookkeeping. We want to have 8 electrons in the outermost shell. So this is the main reason or the main agenda behind all the chemical reaction. We want to have 8 electrons in the outermost shell. So from the periodic table, right, we said metals, group 1 to group 3 are the metals. They are going to react by losing electrons to have 8 electrons in the outermost shell to attain stability. They are going to react by losing electrons, metals. So metals, they are going to react by losing. And then non-metals, here the non-metals, they are going to react by gaining electrons to attain stability. And then the group 8 elements, they are stable, so they don't take part in chemical reaction. Why? Because they are chemically innate. They are stable. They don't take part in chemical reaction because they have a stable noble gas electronic configuration, all these elements, right? And then we explained they are normal in group 4. This one is the non-metal, these 2 metalloids, and then the last two are the metals. So we can use this one, right, to explain. So these are the non-metals, and then these are the metals, right? So metals, they are going to react by losing, and then non-metals, they are going to react by gaining. So non-metals, they can also react by sharing electrons. They can share electrons among themselves so that they will have 8 electrons in the outermost shell. Are we together? And then metals, they only react by losing. It's either they are losing among themselves or they are losing the electrons to the non-metals, but they only react by losing. Are we together? So this is the basis, or this is the foundation of chemical bonding. So we have types of chemical bonding. We have ionic bonding. We have what you call covalent bonding. And lastly, we are going to have metallic bonding. Are we together? We also have another subgroup of covalent bonding, which is called dative or coordinate bonding. So we're going to explain much on dative bonding when we are doing A-level chemistry. For now, just appreciate these 3 ones, right? Are we together, guys? So we explained dative bonding in passing, but for detail, we are going to explain much of it when we are doing A-level chemistry, right? So, ionic bonding. So first you need to understand the definition of bonding. So bonding, chemical bonding, is governed by what you call electrostatics. Electrostatics, right? So bonding is defined as the electrostatic force of attraction between oppositely charged particles. Chemical bonding is defined as the electrostatic force of attraction between oppositely charged particles. So all these bonds, are said to be electrostatic in nature. Contrary to other publications which only say ionic bonds are the one which are only electrostatic. All the bonds are electrostatic in nature. Why? So I'm going to explain that is we are going to proceed with the session, right? So we are going to explain that later. So as for now, we are diving into ionic, specifically ionic bonding, right? So ionic bonding is defined as the electrostatic force of attraction between a cation and an anion, right? At times for junior chemistry, it can be defined as a bond between metals and non-metals. So for junior chemistry, this is correct, but for A level, this is the correct one. This is wrong for A level, right? Why? Because we have sodium sulfate. The sulfate ion is not a non-metal; it's a polyvalent ion. So it's no longer fitting into this definition because the sulfate ion is not a non-metal. But the correct definition, it is the bond between a cation and an anion, or we can say it is the bond between a positively charged ion and a negatively charged ion, right? So we are having metals. So we said that metals are from group 1 to group 3, and then non-metals are from group 5 to 7, including carbon, right? So these are the non-metals. Are we together? So we can explain, so we have the full understanding of the periodic table, right? That's why we spend a lot of time explaining the periodic table, because it is one of the crucial concept in chemistry, right? The understanding of the periodic table. So from the periodic table, this is the group 1, this is the group 2, this is the group 3. So each and every element within these groups is what we call the metal. So we can also further define using this line. But as for now, simply know that you need to simply understand that all the elements in group 1 to group 3 are the metals, and then the rest are the non-metals, except for the group 4. Right? So the bond between these elements is what we call the ionic bond. So whenever you see an element in group 1 reacting with an element in group 4 or in group 5, this is what we call an ionic bond. So let us say you are given that we are reacting element X, which is not there on the periodic table. What are you going to do? How are you going to understand the type of the bond within that given compound? So first you need to understand how to derive the group number from the electronic configuration. So we did electronic configuration, and we defined electronic configuration as the arrangement of electrons in their electric shells, right? So let us use sodium as an example. So sodium is 1123, right? So the electronic configuration, we said the first shell is filled with 2, and we don't proceed to the next shell without complete filling the previous shell, right? So all the other shells are filled with 8 electrons. So for the next one, we're going to have 8, and then we are left with 10, since we are starting with 11 electrons, right? And then we are left with 1. So the number in the outermost shell, the number in the last shell, what you call the valence shell, denotes the group number. And then this number of shells, right? The first shell, the second shell, and the last shell, which is the third shell. So these are what we call the period number. So the period number is equal to the number of shells. So I think we have alluded much on this, and I'm pretty sure that you understand this, right? So the number here in the outermost shell is the group number. So if you are given element X, what you need to do first is to write the electronic configuration and then identify the group in which the element X lies by simply noting the number of electrons in the valence shell, right? So first you start by writing the electronic configuration, and then take note of the number of electrons in the outermost shell. The number of electrons in the outermost shell is equal to the group number. And then we said all the elements from group 1 to group 3 are the metals, and then from group 5 to group 7 are the non-metals. So the bond between the elements in these ranges is what we call the ionic bond. As simple as that. So let us use sodium and then oxygen. So oxygen is number 8 on the periodic table with 16 mass number here. So the electronic configuration for oxygen is 2, 6, right? So for sodium is 2, 8, 1. So sodium reacts by losing electrons in the all the electrons in the outermost shell, because it is a metal. And then oxygen will react by gaining electrons, so that it will have 8 here. So we need to have 8 electrons here. The stable noble gas electronic configuration. So oxygen needs to have extra 2 electrons, and then sodium, one atom of sodium, we will lose 1 electron, since we are having 1 in the outermost shell. So what are we going to do? We are going to use 2 sodium atoms, which will then donate 2 electrons to this oxygen atom. So we can simply illustrate that using the diagrams. So this is the sodium, right? So we can use, these are what you call the dot and cross diagrams, right? The dot and the cross diagrams. And then one electron in the outermost shell for sodium. And then we go on to draw for oxygen. This is our oxygen. And then we use the dots. So if we were to use crosses here, we're going to use dots here. If we were to use crosses here, we're going to use dots there, right? It's only to indicate or to highlight so that you can fully understand the electron transfer, right? And then we are having 6 electrons in the outermost shell, right? So sodium would give away this 1 electron, right? Sodium will donate this 1 electron. And then we are going to have 7 electrons here. And then another sodium atom will do the same, right? Another sodium atom will do the same. And then we are having a stable octet configuration, right? So we have added the two electrons, one from this sodium atom and then the other one from this sodium atom, right? So we're going to have the square brackets. So this is how you illustrate the bonding in your examination, right? So the square brackets, you're going to draw the ions being formed. So we have, in sodium, this valence shell has been lost, right? So we're going to be left with these inner shells, right? These 2 inner shells. So we're going to have sodium, right? And then we're going to have sodium in the outermost shell. Are we together? And then we plot the square diagram. And then we include the charge here. It's a +1 because each sodium atom has lost 1 electron, so it's +1, right? And then how many sodium atoms have we used? We used the 2, so we're going to put a 2 here. And then we draw another one for oxygen, the oxide ion, right? So oxygen is O, right? And then we include the dots, right? And then we highlight the electrons from the sodium atoms using the crosses, right? And then we put the square diagram. So how many oxygen atoms? We used 1, right? So for 1 you cannot include it, but for the sake of understanding, we must include it. And then the charge, how many electrons did oxygen received? 2. And then 2 minus, negative sign indicating that we have gained electrons, we have gained extra negative centers, and then this positive sign indicating that we have lost negative centers. So this is what you need to understand. This one will come in your exam, so you should be able to draw the dot and cross diagrams. And then lastly, we are going to include what you call a key. So key, you can say that X meaning electron from sodium, and then dot electron from oxygen, and then you're good to go, you're done, right? So this is what you need to do for all the ionic compounds, all the bondings. You must include the key. For ionic compounds, you must show the square brackets, right? So let's do another one for aluminium oxide, right? So first you need to aluminium and oxygen. I don't want to write the formula first, so I want you to understand the concept, right? So this one is for aluminium oxide. So we are having aluminium and oxygen, right? We're having aluminium and oxygen. So aluminium is aluminium 13 here and then 27 here, and then oxygen is O, right? And then 16, and then 8 here, 16 here, right? So we're going to write the electronic configuration for aluminium is 2, 8, 3, and then for oxygen it's 2, 6. So aluminium needs to lose all these 3 electrons to be left with a stable noble gas electronic configuration. Aluminium wants to lose all these electrons so that it will have an electronic configuration which is similar to that one of a noble gas. So all the atoms, all the elements will react to have an electronic configuration which is similar to that one of a noble gas. So you must have to compare the resultant electronic configuration to that one of n of the noble gases, right? Alright. So oxygen needs to gain 2 electrons, and then aluminium needs to lose 3 electrons, right? So how many aluminium atoms are we going to use? And then how many oxygen atoms are we going to use? Right? So this aluminium will give 2 oxygen atom 2 electrons. We give the oxygen atom 2 electrons, and then we are left with 1. And then we are going to have another oxygen atom which needs 2 electrons, right? Each oxygen atom needs 2 electrons. And then we are going to have another aluminium atom which will give away 3 electrons. So we are now having a total of 4, right? 4 electrons. So this will give this oxygen atom 2 electrons. And then we are left with 2 electrons. And then we'll give another oxygen atom these 2 electrons so that we can have no remaining electrons, right? So we're going to say aluminium. So we have used the 2 aluminium atoms and 3 oxygen atoms, right? So we're going to say aluminium. We'll draw the electronic configuration in the form of diagrams. So it's aluminium, and then we're going to have another shell, and then another shell, and then we use the crosses, right? And then 3, right? And then we draw another aluminium. Are we together? And then we draw again another aluminium. And then we are going to have oxygen, right? Oxygen with 6 electrons in the outermost shell, right? 6 electrons in the outermost shell. Are we together, guys? Then this, right? And then we are left with this 1 electron. And then we are going to have this. Then we are left with these 2 electrons. And then we are going to have another oxygen atom here, right? And then these 2 then come here, and then this one will come here, right? So you must write the electrons in the square brackets, not here. You mustn't show these electrons there. Why? Because you're still having them here, right? So you must not show them. You just indicate with the electron transfer, right? And now we're going to draw the square diagrams. So for the square diagrams, we're only going to draw the ions, right? So we have aluminium, right? And then we're going to have the outer shell, which is 4. And then the square diagrams, and then 3, the number of electrons each aluminium atom loses, and then a plus sign indicating that we've lost electrons, and then the number of aluminium we've got used 2, this one and this one, and then the oxide ion are going to do the same. So it's O, right? Then we include, and then we say 2 minus number of electrons each oxygen atom gains, and then the number of oxygen atoms we used 3, and then we are done. So this is what you need to know for each and every of the ionic compounds, right? So to write the chemical formulas, so we are having aluminium with this charge, aluminium 3+, right? And then we are going to have oxygen with this oxide ion 2 minus. So to write the chemical formula, we simply use this formula, right? So it's A to the power B, and then C to the power D. So the formula is going to be A, G here, and then C, B here, right? So this one is in this format, right? So it's aluminium, and then here we're having 2 here, and then O, and then here we're having 3 here. So this is the chemical formula for aluminium oxide. Are we together? So first you need to be able to write the formula of the ions, and then you swap these coefficients of the charges. As simple as that. To write the formula for sodium chloride, is sodium plus, then chloride minus, and then we exchange. This one will go there, this one will go there. To write for sodium oxide, is sodium plus O2 minus. This one will go there, this one will go there to give us Na2O. To write for calcium chloride, calcium 2 plus, chloride 1 minus. This one will go here, this one will go there. So it's Cl, Ca, Cl2. As simple as that. So this is how you write the chemical formulas. You exchange these coefficients of the charges for ionic compounds. Are we together, guys? So I think it's very, very clear, and I think you're able to write all the chemical formulas for the ionic compounds. So we're going to discuss on the properties of the ionic compounds later. For now, we just want to appreciate the bonding, how to write the square diagrams, how to show the bonding. So in exams, we are only going to show these square brackets, right? So this one is the working, and it's not relevant unless you are told to do so in your examination. So this one is mainly for the purpose for you to understand, right? But what is important in your exam is to write this square diagram notation, right? Alright, and then we are now moving on to what we call covalent bonding. So we are now moving to covalent bonding. So covalent bonding, it is a type of bonding found between non-metals. It is the bond which exists between non-metals. So we said all the bonds are electrostatic in nature, right? So we want to understand where the electrostatics are within a covalent bond, right? So we're having the bond between sodium, between chlorine and chlorine, right? We're having a bond between oxygen and hydrogen. We're having a bond between all the non-metals. This is what we call a covalent bonding. So they react by sharing electrons, right? There is no gaining of electrons, there is sharing of electrons. Why? Because we are not having metals which will then donate the electrons to be gained, right? So all the non-metals, they react by sharing electrons. Are we together, guys? So let us say we are having chlorine. So the electronic configuration of chlorine, so chlorine is on number 17, 35.5 here. So the electronic configuration is 287. So chlorine needs to have an extra 1 electron to have 8 here, right? So it will then share with another chlorine molecule, chlorine atom, I mean, to form the chlorine molecule. So we're going to have, I'm only going to draw the valence shells, right? So this is the valence shell with 7 electrons, 1, 2, 3, 4, 5, 6, then 7. And then we're going to have another one with this 7. So we're going to share these 2 electrons, right? Are we together? So the resultant compound will be like this. So it's so we can say dot to indicate that it is an electron from another chlorine molecule, right? So we can show this one by dots, and then this one by crosses. Are we together? So this is the covalent bond between the chlorine molecule, between the chlorine atoms. As simple as that. This is what you need to understand. This one is going to share electrons, this one is going to lose electrons, this one is going to... So this is what you need to understand, that all the non-metals, they react by sharing electrons. So go on to have water. So water is H2O. So for covalent bonding, the bonding is mainly derived from what we call the electron bookkeeping. But for junior chemistry, don't allude much on electron bookkeeping. You need to know the structure of the bonding. You need to know the chemical formula, right? So for water, we're using 2 hydrogen and 1 oxygen. So you simply know that oxygen is the central atom, and then this one are the bonding pairs. So one single line indicates a 2 electrons being shared. So it's called a single pair. Pair meaning 2 electrons. So we're having 2 electrons, 1 from hydrogen and then 1 from oxygen, 1 from hydrogen and then 1 from oxygen. So this is the bonding of in water, right? So one line indicates a shared pair of electrons, right? So for carbon dioxide, it's C, double bond O. It's simply that. So this one is the central atom, these 2 are the bonding atom. The central atom at the center, the bonding atom, the one coming to bond, right? So you're having, so 2 lines indicate you're having 2 pairs, meaning to say 4 electrons. Are we together? So you're going to have 2 from oxygen, 2 from carbon. And this one is the carbon, this one is the oxygen, the central atom, right? And then for we have, how many electrons are we having for carbon in the outermost shell? we are having 4. For oxygen in the outermost shell, we are having 6. And then we have used 2, so meaning to say we are left with 4. Right? And then we are left with 4 here. Right? And then for carbon, how many electrons have we used so far? We've used 2 here and then 2 there. So meaning to say all the 4 electrons have been used in the bonding. Right? So this is the complete bonding in carbon dioxide. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. And this one 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons for carbon. This one 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons for oxygen, and we are done. We go on to have another one for ammonia. So ammonia is NH3, right? So nitrogen is the central atom in, and then we're going to have H, and then H, and then H, right? So this is the bonding in ammonia. So we're going to have nitrogen as the central atom, right? Nitrogen bonded to 1 hydrogen, 2 hydrogen, then the third one. So H, H, H. And then hydrogen has got 1 electron, 1 proton. Doesn't have any neutron, right? So this one. And then nitrogen has got 5 electrons in the outermost shell. It is in group 5. So we have used 3 electrons so far. 1, 2, 3. And then we are left with 2. So these are the 2 electrons. And then we include a key. So this is the bonding in ammonia. And then we have another. So you do the same for all the covalent molecule. First you should be able to understand the chemical formula, and then identify the central atom and the bonding atoms and draw the orbital overlaps. As simple as that. So we're going to have another one for methane is CH4, right? So carbon is the central atom, and then we're having 4 hydrogen. So this one is the carbon, right? And then we're going to have these 4. H, 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 and then H. So H, where we're having hydrogen, always remember that you're having a single bond. And then carbon is in group 4, 4 electrons in the outermost shell. And then we have used the 4 electrons, you know, to say we're left with none. And then hydrogen has got 1 electron, so 1, 2. So hydrogen attains what you call the duplet state. 1, 2, 3, 4, 5, 6, 7, 8. And then for carbon, we measure it relative to the octet rule. And then this one to the duplet rule. It's simple as that. This one needs to have 8 electrons, this one needs to have 2. So this is the covalent bonding. The bond between nonmetals, which occurs through the sharing of electrons. Right? So what else do we need to know here? What else do we need to know? So we are now moving on to metallic bonding. So we have another subgroup of covalent bonding. So let me highlight that one before we proceed to metallic. We have another one called dative bonding on coordinate bonding, right? Coordinate dative bonding. So it is a subgroup of covalent bonding. So it is when one atom or when one molecule donates all the electrons to be shared. So here, as you can see from here, we are saying that nitrogen will donate an electron, and then hydrogen will also donate an electron. It's a mutual relationship. So here we are having a parasitic relationship whereby only one atom is going to donate. Only one molecule, is going to donate. So let us say we are going to have ammonia, right, and boron trifluoride or aluminium chloride. So boron trifluoride is an electrophile, which is electron deficient, right? Electron deficient, meaning to say it doesn't have a full octet, a full configuration. It has got 6 electrons. It has got 6 electrons in the outermost shell. 6 electrons in the outermost shell, right? So boron is in group 3. So boron is the central atom, right? And then fluorine here, fluorine. So all the group 7 elements, they form zinc bonds, and then all the compounds where we are having hydrogen forms a single bond. All the group 7, they form single bond in hydrogen. Single bonds, right? So we're going to have fluorine here, and then fluorine here. And then boron has got 3 electrons. And then we are left with this unoccupied region of the orbital, right? So we're having 1, 2, 3, 4, 5, 6. It is electron deficient. It doesn't have a full octet configuration. And then we complete that one for We complete this one for fluorine. And then we are having ammonia. So ammonia, we are having nitrogen is the central atom, and then we are having this one is the bonding atoms. So we are having, and then we are left with another electrons which we call the lone pair. These are called the lone pair. These electrons in the bonds are called the bonding pair. So lone pairs, these are electrons which are not included in the bonds. So this is the diagram for ammonia, like we have illustrated here, right? So nitrogen, or the ammonia molecule, we donate this pair of electron to this one. We share this pair of electron with this one, right? So this is the relationship whereby only one molecule donates all the electrons to be shared. So previously we were saying that hydrogen will provide and then carbon will provide. Hydrogen will provide, carbon will provide. But here we are saying only the ammonia molecule will provide the electrons to be shared. Boron trifluoride will only receive. It doesn't contribute to the sharing of the electrons. It's no longer a mutual relationship whereby boron will provide and then nitrogen will also provide to share the electrons. Here we are having only one molecule providing the electrons to be shared. So this is what we call coordinate bonding, coordinative bonding, right? Only one atom, only one molecule will provide the electrons to be shared, right? So we're going to have the bond in this form. So it's N. So let me highlight this by this so that we won't waste time. And then this is the boron, and then we're having the shared electrons here. Are we together? We're going to have the shared electrons here. As simple as that. So this is how you illustrate the bonding in boron trifluoride. So here you draw the orbitals as usual, the orbitals, and then show the bonding in ammonia as usual, and then in fluorine as usual. But here, that's where the whole issue lies, right? Here, we must indicate that these two electrons are coming from one molecule, which is ammonia. So you must know this bonding from boron trifluoride and ammonia. From ammonia with so this one we're going to discuss much when you're doing A-level chemistry. As for now, just know it is an ionic compound, right? And then we're going to discuss this one, ammonium ion. We also have coordinate bonding, and then in carbon monoxide we also have coordinate bonding, right? So these are the molecules where we have coordinate bonding. So we're going to explain much on that when we are doing A-level chemistry. As for now, just appreciate boron trifluoride. Yeah, just appreciate boron trifluoride. All right. And then we are now moving on to metallic bonding. Metallic bonding. So metallic bonding, it is defined as the electrostatic force of attraction between a sea of delocalized electrons in the metal cation. The electrostatic force of attraction, electrostatic force of attraction between the metal cation and a sea of delocalized electrons. Are we together? So this is the definition for the metallic bond, right? So you must understand that we are having a sea of delocalized electrons in the metal cation. So we have this type of bond between the metals, right? Between them, the metals. So we are having the bond between the metals, and let's say we are having sodium metal. So sodium will lose electron, so it will we are going to have the sodium ion, and then the sea of delocalized electrons, right? This is the sodium ion, the electrons, and etc. So we must show this in a regular arrangement, right? We must show this in a regular arrangement. So it's sodium plus, and then sodium plus. Then we include the electrons. As simple as that. So this is the metallic bonding. So for now we can conclude by only appreciating the metallic bonding, right? And then for the next session we're going to do alloying and to give the physical properties and the chemical properties of the compounds formed by this type of bonding. Are we together, guys? So this is what you need to understand. This is what you need to know, right?